audiophile bricks, magic pyramids to harmonize the work of the bricks, thick cables, super boosters to keep the cables off the floor, warming up cables, sound field harmonizers, and other audiophile gadgets. Oh, and I forgot to mention rewinding CDs to begin with, so that the compact disc will finally sound right. And let's not forget about special slow-blow fuses that improve the sound of your power amplifier while protecting it from everything possible. Dear friends, in this video we will show you how to get high-quality sound from your stereo system without using any magic or audiophile misconceptions. We do this based on measurements and science. We've got Roland here, the lead engineer at Reflector Audio. Roland is the developer of phase linear studio monitor acoustic systems, which make it possible to assess the quality of sound engineers and musicians' work with maximum accuracy. So Roland, what is the most important thing when creating a high-quality stereo system? Let's start with where we are, and we're in a very interesting little room. About 10 years ago at an exhibition in New York, a company called Tetrix approached us. A very interesting team, and we brought our largest reflector set there. An open design, about 10 kilowatts, and the halls were huge, the exhibition was big. And what's interesting is that these guys were really curious about how their products would work with our open design. Because they said they've already tried every possible speaker they could. In short, they actually make a room within a room. You could say it's a complete room finishing. This room finishing, it's not just about putting a couple of absorbers in there and that's it. They actually work with the room itself, and you can basically create a room almost anywhere, and that's exactly what they did for us. We first installed the speakers, and then they organized the room around the speakers. And that's probably the most correct approach you can take, to set up the speakers first and then build the right room around them, or even the right house. And by the way, right now we're in such a setup. We're in a small room that's separated from the main house. It was specially designed so that Reflector Audio bespoke speakers would sound flawless here. The main problem with rooms is resonance at low frequencies. And in this room, the low frequencies that reach the listener's ears pass right through the walls to the outside, so they don't create any standing waves. The mid-frequencies are absorbed by special acoustic wool inside the walls, and there are diffusers on the walls that scatter the high frequencies, which allows for flawless sound. Well, you've just explained everything that happened there. I was surprised myself because for the first time the open design really showed what it could do. And in this room, it's not very big, it's small relatively speaking, but from 25 Hertz down to 0 for an open design with good sound pressure level, you could listen to it, enjoy it, and it was very surprising. They themselves were very inspired. Sound engineers brought their own discs and listened to everything. And many said that yes, now they could have worked on it, meaning they found mistakes, because it's generally very difficult to properly control the low end. Or you sit close to the speakers trying to minimize it as much as possible so that the entire low range doesn't get cut off for you. You've already explained how all of this is set up. This room has viscous walls. Everything that reflects here has a very low quality factor, even at the end of the room. The unevenness is relatively small, but the most important thing here is that we got more than a third of the room. We were able to get the full sound from the speakers. If I show you the measurement, this is the only area where the microphone sees the floor. The floor is the only solid thing left here. Since it heats the floor, we need to somehow maintain the temperature gradually. We kept moving all of this around. He handled the design himself after that. Nearly all the walls are completely viscous, as well as the ceiling. And if you're standing outside and listen, you can hear how the low frequencies pass through. When I arrived and was bringing the lamps here, we were experimenting, and I could hear the rhythm section and the punch very well, right, as I was walking here from the car. Yeah. Each area has different absorption. Some areas have more absorption in the mid-range. Some have more absorption in the low end. A bit of reflection has been added, so you can at least more or less feel like you're in a house and not, let's say, somewhere in a completely anechoic chamber. So, but it all works. It's all very nice. It's very pleasant to be here, and it's great for conversation. The frequency range here is roughly from 25 to 0 hertz, with variations of about plus or minus 1.5 to 2 decibels. That's studio level. Yes, and there are no influences, except for this floor at 252 hertz, at 250. Let's say hertz, the 2 doesn't matter that much. We can see it, and there's a small reflection. Of course, you could try to cover all this with a coating on the floor, but this frequency is very difficult to... And we'd reduce the small unevenness there, but not as much as we'd like. So that's why it practically doesn't affect anything at all. As for the phase characteristics, on our graph, the upper curve is the phase characteristic. It's labeled phase. You can see there that the phase is trying to break through. And right at the bottom, we can see that in this spot, there's a very narrow, small notch. Yeah, well, that's how reflections work. Now I'll play this same speaker for you, but in a different room. Here you go, take a look. So this is the speaker. What's going on here? The entire range is almost the same in terms of amplitude frequency response. There's very little difference, but the phase is just completely broken up into pieces. So basically at a low frequency you get a buckshot, not a bullet, buckshot, and this buckshot, this blurry low frequency range, will be perceived as blurry. It will be very uncontrollable and unclear. On some notes it will be shouting, on others it will be calm, and still others. You can't understand what's going on. Whether it's the cables or not, everything is visible. Next, I can show you in the same room, but in another corner, the speaker, the very same one. Take a look, pay attention to the red characteristics. At the top is the phase. Look, it doesn't even match the left speaker. Imagine your speakers each working fine alone, but not together. And not only that, look at the amplitude frequency response. See those dips? It's useless to try to correct that. That's what the influence of the room means. So the room is actually one of the most important factors for getting quality sound. Not cables, audiophile bricks, or miracle harmonizers. That comes later. So why reflectors? What are they? How do we work with them? What were they created for? One of the ideas behind reflectors in general, there you see the 18-inch reflectors standing in the back. Reflector Audio Bespoke. These are bespoke systems. Their job is to shine like a spotlight, beautifully like the lamp in your car shines, precisely adjusted. This entire area is well lit with no dark spots or anything like that. Here, several implemented ideas have been incorporated, which I always try to do and see the results, how things turn out later. So first of all, I used ring interference here. What does that mean? We have a mini sample here. A mini sample? Micro. It works. By the way, if you plug a phone into it, it even sounds good. What's the idea? First, all these magnets are in the front, right? So basically, when the diaphragm emits sound forward, it doesn't see any of its own side reflections from a single diaphragm because the center covers all of that. Next, why are they arranged like that? This distance here, if we take them on a plane, we can make this distance up to half an octave or even a whole crossover frequency higher. For 18-inch speakers with a light diaphragm, that's really good, and even more so for tweeters. The crossover frequency here is 10 kilohertz. Why is it called ring interference? Each of these speakers at the corner cancels each other out. If we leave it like this, it will only cancel here, this one only here and here. And then if we measure, we'll get quads. That is, in some places it will cancel, and in others it will actually be in phase and we'll get 4. That's why one of the tasks was to absorb its own sound. Then it absorbs the reflection, then it absorbs the open design, and the figure 8 finishes its job completely. And in the end, we get 35 degrees. That's 35 degrees. This spotlight is shining. The pressure drops from the sides, and that's it. There's nothing there.
So it's narrowly directional.
Very narrowly directional, yes.
And that alone already minimizes the influence of the room on the sound quality.
The wider the directivity pattern,
the greater the influence of the room.
It's not perfect in the sense that its phase characteristic holds only within those 35 degrees. It's very difficult to keep the impulse, the radiating impulse, steady. It's practically a challenge in every direction. A tall order. So here, within 35 degrees, the phase stays the same. Later, the phase will change. But further on, the radiation from these speakers drops off a lot. But with the square 2, that's exactly where my whole idea is implemented, to fully preserve the phase. You can also measure it at 90 degrees and even behind the speaker. The impulse stays the same, even though the amplitude frequency response has dropped. This primarily indicates that this is a true radiator.
And a narrow directivity pattern.
The square 2 has a narrow 45-degree directivity pattern.
I want to explain a little about narrow and wide radiation patterns. The most important information from the music that we receive comes directly from the speaker. So if we take the speaker like this and listen to the direct sound, that's the direct signal. If we have phase linear acoustics, it means that we will get accurate information, just as it's recorded on the track, just as the musician plays the note. As soon as the radiation from the wide radiation pattern starts hitting the walls, the floor and the ceiling, the signal path gets longer. This means that part of the signal will reach us with a delay. This alone blurs the musical image, blurs the texture of the sound, and blurs the stereo panorama that we want to hear.
And with a different phase characteristic.
And if the speaker is not phase linear, then the phase distortions that are already present in the acoustic system, when they hit the walls, floor, and other objects, get distorted even more. And as a result, instead of high quality sound, instead of good music that pleases the ear and the soul, we end up with, excuse my expression, a mess.
Now about the main point. The main thing is how to connect two speakers, the high frequency and the low frequency ones. I just want to say that we have a different approach and we don't use the filters that people are usually accustomed to. I understood it in my own way and even developed it further. From a practical point of view, it's more clear to me than reading books and making the same mistakes that have already been made. Therefore, the feature of Square 2 filters and the whole approach, what did I draw here? This is acoustic power, measured by multiple measurements. You can read about it. Each company worked on this, and each approach was different. JBL had one approach, Yamaha had another. JBL polished everything, Yamaha's was all crooked, but the result was still the same. Theoretically, it can also be slanted. It all depends on you, right? At the top, that's the area of the diaphragm, plus X-max, that's the speaker's displacement in the room, plus amplifier gain at low frequencies, because boosting the lows, bringing 20 Hertz up to the level of 60 Hertz, that takes a crazy amount of power. So that's fine, just read Linkwitz, it's all explained there. The most important thing I want to convey to you is that I can draw a crossover anywhere here. It doesn't matter where the crossover frequency will be. I'll just explain the main idea. So this is the low frequency crossover. Low frequency. This is the mid frequency crossover. Mid frequency, mid to high frequency. Anywhere, if you're making a crossover, your goal is to get the maximum drop right here. All reflector audio reflectors have at least a 36 decibel drop. And let's say the third band we have, There it reaches almost 50 decibels drop. What is this needed for? This graph is self-explanatory. You have the larger the diaphragm area, the smaller it can be. At high frequencies, this can work, right? But with everything we've just told you about angular characteristics, about all these things, with this approach, if I create here the same crossover as this one, then at acoustic power, it makes perfect sense. So at acoustic power, we'll get this kind of result. Why? Because you're violating the top graph here. To the area of your small diaphragms, you add the area of this radiator. Even if you phase it on the axis, it doesn't matter, because there will be interference on the angular characteristic. So if you have two speakers, you'll get interference. Even if you have a coaxial speaker, you'll get interference if there are any inaccuracies. That's why making yours like this is very difficult, because you'll affect the impulse response. The impulse response will be terrible. That's why everyone should
go and ask Reflector Audio, and they'll do what you need, so you won't have to struggle.
All Reflector audio speakers have an acoustic filter. This is the basis of the square 2 resonators, orifices that are adjusted in a certain way and then have a chamber.
And this is the front panel, which has a very unusual appearance.
And look and shape, yes.
And when you look at it, no one can figure out what kind of front panel this is or what kind of speakers are placed there.
We'll show you the square 2 crossover now. I can show you the crossover for the third band. And we have a third band, but there are never any subwoofers on the third band at the crossover frequency of 300 Hertz. And this is a 3-band open design system. Here you can see what kind of roll-off there is. We're showing these graphs. Some say that there is an opinion that phase distortions are not audible. They're not audible.
Not audible, they're not.
I kind of agree.
You can't hear them until someone tells you how to listen for them. And I'm using this special word from Roland's vocabulary because Roland told me how to hear phase distortions. It's very simple.
If you're trying to make a phase linear speaker yourself, you can make it from some ready-made speakers that are already being sold. So you made one, and now you have it set up, one that hasn't been modified and one that has been modified. I assure you, you won't even need, even a deaf person would see it and a blind person would hear it. The difference is that big. Why does this happen? First of all, don't forget that this is the equivalent diagram of all the frills we've got there. The cables, the speakers, all the components we use. Yes, impedance as well. All of this has an effect. If you make the phase response linear correctly, the speaker won't have that many components and it won't affect the impedance as much. These filters affect it. That's already one indicator. Next, these gentlemen who are always messing around with DSP and processors, they distort the phase response and listen to it. Guys, don't waste your time on nonsense. I'll explain why. It's the same as listening to correlated and uncorrelated pink noise. So while you're listening to it on one speaker, there's no difference at all, but on two speakers, it's just insane. That's why you need to give your computer a task so it understands what you're doing. I've already said that if someone modifies the speaker, both the first and the second one, you listen to them. The only thing I want to tell you, again, maybe it's my personal quirk, is that I have this concept of leader and follower. Almost all the speakers we have, hundreds of thousands of them, all of them, with a small exception, about 1.5%, have a leading tweeter. This is the first mistake that actually relates to speaker production. This is the first nonsense of the audiophile world. The thing is, with the right approach and a flat, well, the objective is to get a flat response phase, undistorted. Your main driver should always be the low frequency speaker, everything below. Bass, mid, treble. If you remember, or if someone checks online, a couple companies tried using a big speaker at the top, followed by several smaller ones, and a tweeter on the floor. I won't name the companies, but you can find them online. At least people tried, thank God. So, this concept, when you get it into your head that your main speaker should be a low frequency one, not the other way around. Why does this happen? Because with a flat phase, all your speakers are here in the room. There's no trickery. And in other cases, if your tweeter is leading, your woofer will be in the next room.
This causes a blurring effect and lack of clarity in the low frequency range.
I'll talk more about this later as well.
Can I explain how to tell high quality from low quality sound?
Well, go ahead.
I'll tell you about the 4 laws of audio engineering. I just came up with them today.
All right.
How do you know if your music is high quality? The first criterion you need to pay attention to is the frequency response of your speakers. Often when we're at home, we can't check it. Well, not everyone has a microphone equipment to measure all this or a special test signal at home. That's why you can determine it by ear. Just turn on music on your sound system and start listening. And the most important thing you'll hear is balanced frequencies, distinct low frequencies, a clear mid-range, the vocals, and good crisp high frequencies. And such music, such sound won't cause you any discomfort. That's the first thing you need to pay attention to when listening. The second law of audio technology is the texture of the music you hear. As a rule, any piece we listen to consists of several instruments. For example, guitar, cello, vocalist, double bass. On a low-quality stereo system, you will never be able to hear each instrument's part separately, which in the end weave together into the overall composition. It's simply impossible. But when your acoustic system and all its components are phase linear and are in a properly acoustically treated room, you can easily hear each instrument's part without any effort. This is a very clear and precise sign that the system sounds high quality. The third law of audio engineering is stereo imaging with depth layering. When your system is in a treated room and it is phase aligned with a flat frequency response, on good high-quality recordings, you will definitely hear separate images of the musicians, which will be positioned at different distances from the listener, from you. And this is already an audiophile criterion. It means that your system already sounds very good. And the fourth final law of audio engineering is speed. It is directly related to phase, which we are telling you about today. Because every note has a beginning, a peak, and a decay. Take a simple composition for an experiment or just your favorite song and play it on your laptop through the laptop speakers. And you'll only hear the peaks. You won't hear the beginning of the note. You won't hear its decay. But when your system is properly tuned, you'll hear how each note is born, reaches its peak, and how it gradually fades away. And the most interesting thing you'll hear is that during the playback of your composition, you'll hear several previous notes that are still fading away while the new note is being played by the musician. And that's exactly when the introduction of the fourth criterion enriches the perception of music so much that you simply realize this is true audiophile sound. Speed and phase are the same thing. Because when we talk about phase, we check it using the step response. How is it checked? An impulse is sent to the speakers like this across the entire frequency range from 20 Hz to 20 kHz. The step response should look like this. See, our impulse started and then gradually faded out. That's how it should be. What happens in a $100,000 speaker? The impulse played, and look at this mess. First the tweeter fired, then the mid-range speaker for some reason started firing with a delay and against itself because it is below zero. That happens. And the third bump is the bass speaker firing. It fires with a delay. That's what Roland was talking about. It's in the next room. So you'll get the feeling that it's been taken somewhere farther away. And as a result, you'll get this. But
your eyes see the speaker, that's the second trick.
your eyes see that the speaker is here,
but actually it's not.
You have a blurry texture, you have annoying frequencies, you have a completely unclear stereo image.
The tweeter is leading.
And you won't hear any speed. Because all the drivers fired at different times, and they also fired in different directions. And therefore, before I give the floor to Roland, I want to formulate the 0th law of audio technology. The sound in your stereo system should not annoy you. Roland?
To continue, there's a speaker called Martin Logan. I've modified it several times, both the large and small ones. There are various sizes with 8, 10 and 12-inch woofers for low frequencies. Why is it interesting to modify them? Because usually everyone complains about them. The thin film inside makes a screeching noise, and the woofer in the back just sits there crawling around, and there's no real sound.
I had the same problem with Martin Logan's. Yeah, that's right.
See, that's good, but you have to do it right, of course. That's exactly why I want to tell you about it. For those who want to understand what we're talking about and redo it, there are all the right ingredients, the kind of thing I would like to achieve.
What are you trying to achieve?
First, it's important that the woofer is close to the floor.
A sealed enclosure.
It had a ported enclosure, but that's not really important.
I had a sealed one.
Ah, well, okay, it doesn't sound good. But when you find the tricky filter there, you have to dig into it, explore, and you can separate it and connect it to the processor with amplifiers. It doesn't matter which ones. What's important is that you know what you are doing. Do it, try it, assemble this system. Using parallel compensation for amplitude, frequency, response, and phase. It takes time to explain, but it's actually quite simple. This is my method, and you won't find it elsewhere. You smoothly match the film with the bottom, with the speaker, and this match will be, I recommend, in the range of 600 to 800 Hertz. When you match all this, I'll draw you the stepper response impulse of this Martin Logan speaker. Martin Logan. There you go. So the tweeter, the mid-range out of phase, and the bass.
Wait, it's a three-way system, but it's actually a two-way.
It's a two-way. But why is the mid-range part with inverted phase? It's a high-frequency section because...
But when the film fires, it fires unchanged.
No, but you have a filter installed. This is one way to bring this point closer to this one with inverted phase, to create this section there. This is a two-way system. When you do it another way, your impulse will look like this. It doesn't matter going forward. This axis here and this one too.
This one is also good.
This is 0, 0 for us. This is with inverted phase. So when you do this section like this, you won't hear anything at all, because the reason I say that the higher the frequency, the more this section is split up at 600 to 800. At 800 Hertz, the section will be right here. The lower, you'll also use this method, that's it. But you'll finally hear that this low frequency speaker is very fast.
Well, you really surprised me that with Martin Logan, which is a two-way speaker,
you can provide measurements. We'll display them. Once we have them, that's it.
Yes.
All right. So this section here, the mid-frequency filter, that's how they made it. There are several ways you can do all this. That's the way they did it.
If you take Martin Logan, it's quite possible to achieve a correct impulse response with it.
You'll be surprised. The bass just comes alive because it finally became the leading part.
But I managed to place my Martin Logan speakers near the wall, so they started to sound good.
Well, that's because of the upper bass.
But initially, when I first started setting them up, I had a problem specifically with bass delay. I had that feeling.
Yeah.
The highs and mids played separately, and the bass was totally out of sync. But then I moved them closer to the wall, and everything started to sound pretty good. Martin Logan is excellent with detailed, elegant acoustics.
When you do it, it's clear that it's a film. You have to sit. Just standing up or sitting down will already cause interference, but that's not the point. The point is that you can assemble it and it will surprise you. That's all.
contact us immediately.
You think? Well, okay, here you go. The most interesting thing is that there was a call and they said some guys from America want to meet with you. They're working in Budapest and they want to meet with you. When are you available? Well, we made arrangements, that's basically it. The guys arrived and I didn't know who they were at all. They just showed up and right away they said, well, we've, for the impulse characteristic, show us what you promised online, show us how it all works. On the square two. Well, I showed them everything myself, that I don't change anything, all these characteristics, that's all. They were happy, took the speakers and left. A month later, measurements came in. It turns out these guys are involved in these kinds of problems. The effect of the speaker's impulse on the room's reverberation. They work with connection and T60 measurement. Of course, I could reach out to Yuri Saprovsky, but honestly, I just haven't gotten around to it yet. And here's what turned out to be interesting. That's actually why I did all of this myself. I didn't know it would turn out like this. In short, they made a measurement compared to Neumann KH. The KH is a series of three-way studio monitors.
It's built to standard.
And here, according to the measurements, you can see this phase characteristic, the square 2. Ours is the purple curve and the blue one is the KH curve. Now I'll show you the most interesting graph, the impulse response graph in a room with an added absorber. Red is our square 2 graph and purple is the KH curve. The difference in early reflections is just colossal. If I suspected, well, I couldn't measure it, but from practice, when I do voiceover work, since I do voiceovers, I could hear all of this. It's very refined. So here's the conclusion of these guys. They make studios there, and in translation from English, it's just cleaner. The impulse characteristic of the square 2. It doesn't make the room sound more muffled than the frequency response. It just moves all the reflections outside the critical time window, making them quieter and more even in intensity. In my opinion, this is the ideal situation for a recording studio. Exceptional frequency response from the speaker, but at the same time reasonable decay time. In the room, the sound still feels and sounds like a real room. Unlike some, which are overdamped in the studio by dampers, the frequency response makes the speaker sound like it's in a fully absorbing room. Don't be scared by that. These right away, these are studio speakers, but guys, it's nothing. All this is for anyone, for any room. A speaker should sound the same in the studio and at home. You should get all the pleasure. You should get what you paid for. And this is where it gets really interesting, because let's say we show how the square 2 sounds. I'll show it in a simple way. It sounds like this. It projects in all directions. It shines like this, like little flashlights, while a smooth classic speaker sounds like this. There you go.
It radiates in all directions.
In all directions differently, with different phase characteristics, different impulse, and they came here because...
And when we hear all this, we
get it through the reverberation of the room.
We get a mess.
And we don't understand.
Unintelligibility.
And we blame you and a faulty tweeter.
And a feeling of discomfort and something else, you know. And guys, magic cables, harmonizers, audiophile bricks, miracle pyramids, none of that will help here. They have nothing to do with truly high quality sound or high fidelity. You need a good room, you need speakers with a flat phase response and good recordings.
Next, those guys listened to me, broke the phase, then listened again. At home, set this up. Let's say you take a microphone, stand in front of the speaker, and you realize sound recording, it's just pressing a button. It's basically either everything or nothing. There aren't impulses you can hear because the attack is what's important. And let's say those sharp words like two, yes, those words. When you speak into this speaker, the one with the even face, you'll just hear your voice amplified from behind, that's all. When you speak with the speaker that has a distorted phase, the first thing you'll notice as you increase the volume is that you'll hear more echo in the room. It increases slightly. Yeah, I'm telling you this from experience, and I just got confirmation from the guys from America who are building this studio in Budapest. Next, if you're planning to record a small jazz band, you basically... When you turn up the volume, it sounds really good right now, a jazz band without amplification. As soon as you turn up the volume with a bad speaker, you can even throw off the musician's rhythm. That's how big the difference is.
I can't stand listening to music through speakers at concerts. It's terrible.
Because it's different.
That's not music at all.
You know, you can put it simply like this. You play the grand piano, but you hear an upright piano. That's basically the difference. So,
passing good music through acoustic systems with a non-linear phase response means getting ground meat instead of a steak.
And here's another piece of evidence. We recently had an event with the company Reiko Synths. They were presenting new electronic instruments. My task was, this was at the Reformers venue in the old studio at the Reformation Church. We have a good church with perfect reverberation there. Everything is recorded there. All the classical music is recorded there. And classical concerts are held there too. So it's interesting. And there I had the task of working with a grand piano. I needed to combine and amplify it together with electronics. So the musicians came from abroad and they played the grand piano or the electronics, sometimes with one hand, sometimes with both hands, however they want. But any performance there in that room with a regular classical speaker will only increase the reverberation in the room and there will be no clarity at all. Alexander Wojciechowski was the sound engineer. Well done. Always the work was top-notch and my task was only to find, present, amplify all of it and set everything up. So once again I was working there with the background sound. You can see in the photo, this is just the beginning, just rehearsals. Only the musicians had arrived and 2 more joined later. The speakers are placed behind the musicians. And if this pianist, while playing the piano, has a monitor set up for him at the same distance as the square 2 is standing there, there was a 3-way speaker system set up for this room with ceilings almost 8 meters high. And all of this worked from 25 hertz. Everything went really well. With electronic music, you can't cut anything out. The instruments themselves, it's just everything, all of it. When it breathes like that, God forbid he would have asked you to turn off that background sound, because I can't play when someone's interfering with me.
Someone else?
Someone else. And they all played without any problems. Moreover, the piano was additionally given a ribbon mic. There were several ribbon mics set up and it was additionally mic'd in this hall, and all of this together created a completely harmonious sound. Well, it just wouldn't have worked out with the other option. Imagine if we'd added more mics to such a reverberant space. It would have been unbearable to be there. What kind of concert is that? Well, in my notes, I've written down my attitude towards high-fidelity equipment.
We constantly hear about uncompromising solutions, carefully hand-picked components, incredible exclusive speaker materials, and all sorts of things like uncompromising finishing materials. Roland, what do you think? How does all this affect the sound?
I'm going to surprise you now. All speakers sound good, all of them. The whole problem is with us. And it's all about what you're capable of, what your attitude is, whether you're able to perceive things the way people tell you, or if you actually have your own opinion. Literally, all speakers sound great, so that's it. What? Why?
You really surprise me.
Yes, why? So that's how it is for me. For me too, I might surprise you, but basically we need to go back to the old ways to everything. Everything was done very correctly. The name was right. High fidelity sound equipment. And if I break down this high fidelity sound in today's terms, it will have a completely different meaning. The first thing that matters is the impulse characteristics of the speaker, a simple impulse, a step response, the angular characteristics of these impulses, the change in T60, the amplitude frequency response, the sound pressure level, and distortions.
Wait, but we were told about hand-picked components.
This is a process. Wait, I'm already talking about it.
These are uncompromising solutions.
So all of this goes first. There won't be this. It all goes from the very beginning, what I'm talking about, and only at the end will there be the company name. Do you understand how it works? And how do we listen? The company name comes up and we rush to listen.
An uncompromising solution.
Yes. The Riga 11 portable tape recorder with 6 dynamic wideband speakers. This is the first one you can say has high fidelity in its sound. It's in a different class because its sound pressure level is low, the amplitude frequency response is low, and maybe the angular response is a bit different. It doesn't matter here, but it's the first one on this path. Old televisions are also on this path. They can reproduce what's been recorded. Now, if I draw some basic things you've seen your whole life, let me draw them for you. The test pulse of the amplifier, A.
Meander.
Perfect. God forbid if it's like this here. Sometimes there's no attack at all, then suddenly it just screams and that's it. But when the acoustic system gives a test impulse like this, for some reason everything works damn fine for all of you. So that's the foundation. If I stand in front of the mirror in the morning, I see myself, not my neighbor instead of me. Even if he's handsome, that's my neighbor, not me. That's the foundation. And actually there's less talk needed, right? Follow the plan I've given and you'll hear everything clearly, how this phase changes things. So out of all this nonsense that's out there, only a couple of companies can actually be listed under this level of high sound fidelity. The rest, that's how it is. So then there's a lot that falls off then, absolutely. You understand, right? Starting with cables that twist and turn, anything can happen. But they should be good. They have to be good. Good ones. Not insanely good, just good. Just good. And then your vinyl records sound good, and this sounds good, and that sounds good. But you must be ready for the fact that you don't need to be sound engineers, yet you all try anyway. Then the highs are too sharp. Or if you have questions, turn on the analyzer and check the recording. That's why, thanks to the fact that there are presets here, we can, for example, listen to old records with correction, with the correction of the amplitude frequency response itself. And rock music sounds just wonderful, because there aren't those distortions here that we talked about, right? And everything you do, let's say you only help with the equalizer, it helps if you know what you're doing and the room or speakers aren't an issue.
There are no problems here.
It helps. It helps you hear that rock, the one that really hits hard. So I had this idea. This is a panel. It's taped up here for now because
it's a working prototype.
We're working. It will all be taped up. Everything will be ready. There's nothing else here, but you only solder 2 wires. Maybe I'll also add an output here for adjusting the highs, and I'll add the components that can be used to increase it by half a decibel. You can insert this panel into any case from 15 to 30 liters, whichever you have.
30 liters sounds the best, that's right.
We have a 70 millimeter phase meter, a classic 70 millimeter phase meter whose diameter and length are also standard. You can buy all of this at your preferred shop. If you already have a case about these dimensions, with 15 liters, the bass will be a bit less. But maybe your room is small and it boosts the bass, and that might be enough for you, because we have options. Well, 30 is better. There were other options, but 30 will work. Let's continue. We'll make a few copies of it for now. Later we'll produce the series so that it can work properly, work the same in 15 liters as in 30 liters, even in a small volume. That means here a push-pull speaker will also be installed. So that's why there are two options. It's 8 ohm with a linear phase characteristic. You install it either like this, because right now, as you know, the bass is leading, or like this, with this part facing out. With a low frequency driver as the main one, your entire soundstage will have a linear phase characteristic. It has 30 degrees. It maintains phase when you sit and when you stand. You can stand up and the phase won't change. If you turn it upside down and stand up, you'll get the sound that everyone is used to hearing. In this case, your phase response will be exactly inverted. If you put the tweeter on top and make it the leading one, you'll hear exactly what you all hear, the tweeter in front and everything else behind. At the same time, the amplitude frequency response won't change, but the phase will. That's exactly the catch here. You have to do everything correctly, and it's less of... it's better to do everything yourself than repeat others' mistakes.
Pay less attention to all sorts of myths. I haven't told this story of the tweeter yet.
I haven't told it. This is a tweeter. It has a wide-mouthed horn. So this tweeter has a ring radiator. There's no dome here, which means it's free from all dome resonances. Since it's a horn type, nothing is lost. Its amplitude frequency response is set specifically at -2 decibels in the tweeter itself.
If you hadn't told me, I wouldn't have known.
And you wouldn't notice because it's a horn tweeter, specifically a wide mouth one, meaning there's no combustion chamber, as I call it, no compression chamber. So what happens is the coil is glued directly to the ring at the top, and that's what emits the sound. So there are no transitions at all, no breaks in the material or anything like that, right? That's why the material here is a special kind of film, not metal or anything like that. So the woofer itself is 50 watts, the system is 8 ohms, that's quite enough. The system sensitivity is nearly 89 decibels, 89.1,
something like that.
Exactly. So, here's a suggestion. You see, the thing is, we have options. When you make a whole column, the price goes up. Here as well, because it's made in Latvia, we can't do anything to make it cheaper. We'll have a set price. We'll end up somewhere around that.
Check the link in the description for photos, technical details, and the price. You will be able to see the price for the panel without the case. And then you can make the case as you wish, or install this acoustic panel. You can put it into your existing speaker, a bookshelf speaker, a floor standing speaker, or mount it in the wall.
You will learn from your mistakes, but you will have already completed the first stage. You will have a linear phase.
It has a linear phase.
A linear phase
Panel with a flat amplitude frequency response.
Your task is not to ruin this amplitude frequency response with all the internal reflections. That's it.
That's why we dampen the enclosures.
And you, even if you have a four-legged one, if you're so inclined, you can insert it however you like, it doesn't matter. The speaker handles it. Its Q factor is 0.56, so you can confidently insert it. Here you go. So everything's kind of here. For those who called give recommendations on how to make the phase response flat, how to make it sound good. As well, of course, I can't give you that recommendation. That's kind of my thing, right? But I can give you a hint in the form of a riddle, like this. If you've done measurements, you'll understand what I'm talking about. So your task is to send the speaker you have into the future and then pull it back with the characteristics you need. That's it. It's very simple. Well, actually, to get to this point,
it takes a lot.
I had to go through a lot, so we got carried away talking.
It's all good. Roland, I don't have anything else planned. I just have the conclusion left, but how should I wrap it up? Well, guys, use critical thinking when making decisions about purchasing various audiophile gadgets, such as audiophile bricks, cable boosters, or harmonizers. Because all these souvenirs are nothing more than souvenirs, and today Roland and I have told you about the truly fundamental things. That's all for now. It was Arkady and Roland for you. May the force of great sound be with you. Come visit us. Thank you, Roland.
All the best to you. Thank you.